Hello, in this video I will be talking about one of the more simpler subjects of calculus, the limit. Without it, all of calculus collapses. The limit is the idea of approaching an input value of a function, but never actually hitting it. Let's get right into an example. If you look at a function like f of x equals x minus 1 divided by x minus 1, you'll notice that this function is obviously not defined at x equals 1. But if we approach this value of 1 from both sides, it appears to approach the value of 1. This is the idea behind the limit. Try going very close to the input values from both sides and see what the output value approaches. The reason we approach from both sides is just in case we run into a discontinuity like this. The limit at 1 from the positive side is 1, but from the negative side is 0. In this case, the limit at 1 does not exist. The way we write down the limit is we write down an LAM, then below it we write down our variable approaching the number we want to approach, and then our function. This even works for functions that are defined everywhere. For example, the limit as x approaches 3 of x squared is just 3 squared or 9. This is, as I said, pretty simple. But is there any way we could write this down just slightly more rigorously or mathematically? Say someone claims that if you input a number into a function, say c, they claim that the limit at that point is L. And you want to verify this statement with more than just a calculator and a graph. You should be able to get arbitrarily close to L, so let's set an upper bound, say epsilon, since it seems that mathematicians have a bad habit of choosing Greek letters for their variables, that is greater than the distance from the function and the limit, or epsilon is greater than absolute value of f of x minus L. It is greater than 0, since if it was 0, then f of x would be equal to our limit, which is only true if the function is continuous at that point, but we want to be able to also find the limit of a function when it is discontinuous at that point. Now, if we could always find a corresponding delta, which is always greater than the distance from the x value and the limit, or delta is greater than the absolute value of x minus c, it is greater than 0, then congratulations, the limit exists. This obviously would not work for a function like this, since epsilon can never be smaller than 1, so there will not always be a corresponding delta. Therefore, the limit of this function around that point just doesn't exist. Now we can back up any limit claim with a slightly more rigorous answer. Now, as I said earlier, this notion of a limit holds up all of calculus, and so understanding the limit will be a great foundation for understanding all the rest of calculus. Thanks for watching.